Hello.
Yes, 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 we can watch you, Dr. Ali.
Ah, okay. Okay. So uh, let's start our lecture about neural network algorithms. In fact, this meta-heuristic optimization method is recently developed in 2018, and this is my first time actually presenting these algorithms in English. So excuse me if my English is not very fluent about these algorithms because this is my first time, and I hope I use very good grammar and language so to make you understand about this algorithm. Also the first time I make the PowerPoint because so far there would not be a chance to attend in conferences or other congresses to present the neural network algorithm. That's why. So let's share my screen. So can I turn off my camera because I think my speed today is not very good. So I'm worried in the middle of my presentation the speed is very. So I turn off my camera so you can hear my voice better.
Yeah, it is okay.
Okay. So so now I shared my PowerPoint. You may see the PowerPoint now. Is it okay? Yeah. Okay. So the idea of neural network algorithms, as its name suggests, comes from the artificial neural networks. In fact, the name of the NNA is very similar to ANN. Sometimes people make mistakes the NNA as ANN. In fact, for our reviewers, some of them not some of them, one of them had a mistake to confuse between the artificial neural networks and the neural network algorithms. And although we explain a lot about the optimization methods, it is the optimizer, so it is going to find the maximum and minimums. It's different with the ANN, and the application is different. So finally, at the end, the reviewer is justified about the performance and the novelty of the algorithms. So, as its name suggests, it comes from the biological nervous system, as the artificial neural network does, and the concept, the initial concept, comes from the unique structure of artificial intelligence and its operator for predicting any solutions. As you know that the artificial neural network is a computational model which tries to map the input data to the output data. In order to reduce the error between the input data and output data. So we call the output data in the neural network algorithm as target data. So in fact, it's a kind of minimization problem inside the artificial neural networks. So initially, they use for example, the backpropagation method, reducing the error by the first gradient, something like that, and other approaches. So I'm not very expert in artificial neural networks, in fact, but I somehow know about the processes, but in detail, to be honest, I'm not very expert in ANN. So, but based on my thought about the ANN, I was thinking, why not we use the artificial neural networks to find the minimum or maximum objective function value. So why we should always predict or estimate. So that's why this was the inspiration of developing NNA. So yeah. So talking about the human brain, you know that there are billions of neurons in our brain, and they are very complicated computational units, in fact. So they are consisting of the neurons, the axon, and the axon and the terminals. So the input comes from the dentries, and the dentries from the cell body comes from to the axon, and it is considered as the output. So the inspiration of the artificial neural networks comes from how brain works. So that's why they made a computational model based on the input and output and train the network. So this is the concept of the artificial neural networks, and so they inspired by the biological neural networks and about how the brain works. So they try to model the performance of the brain in calculating for example, the estimation function. So the task was like this. So there are two networks in artificial neural networks. So you may know that some of them are expert in artificial neural networks. So these slides are very basic about the ANN. And you can find this kind of slide in any website, in Google, internet. So it's very easy to find this kind of information. So as you may know, there are two artificial neural networks, feed-forward and recurrent artificial neural networks. In feed-forward, we don't have any feedback loop and the information flow directly. And there is a kind of unidirectional approach from the input to the output. As you can see in figure A, we have, for example, 4 inputs, and this is the input layer, and we have the hidden layers here, and we may have several hidden layers. So, and finally, this is the output layer. So in case here we have only one output solution or one response. In this case, the inputs just follow in these directions. So there's no feedback loop in the process of this feed-forward ANN. But in the recurrent ANN, we have a feedback loop. So in this feedback loop, so you can have some feedbacks from your output to the input solutions. So in this case, somehow the algorithms, so I mean the model, the computation model, can improve itself by getting some information by its feedback. So this kind of flexibility, the recurrent ANN, they have this kind of flexibility. But there are some weights in the links they know, and these weights are randomly generated. And but in the recurrent ANN, these kind of weight values are fixed and they don't change. So so in the recurrent ANN, we have this kind of problem with the weights. Regarding how NNA mimics the human brain, so it's fairly complicated, in fact. But to say something about how this kind of computational model works, so we have in fact the ANN composed of several nodes, or we call it neurons, which imitate the performance of neurons. In fact, we call also this kind of nodes neurons in the ANN, so there's no difference. So in fact, in INN, we call it neurons at the same. Is the same. And these kind of neurons are connected by links to other neurons in the other layers. And also, these kind of nodes or neurons are kind of summation functions, and based on the which function we choose, they act for they try to map the input data to the target data, and also each link also is associated with the weight. In fact, in fact this kind of weight depends on the in the ANN, these kind of weight are initial and random, and by changing the weight, you can change the value of your accuracy. So in fact, you can minimize the differences between the target data and the input data by changing the value of the weights. And sometimes you can use the evolutionary optimization algorithms in order to reduce the weight values. So for example, ANN with GA, ANN with PSO, and this is not a big deal these days. So maybe 10 years ago, many papers published based on this concept. But these days, it's not a big deal. Otherwise, your problem is a kind of unique problem. You have a very good data. Your application is new. In this case, makes sense to join GA with ANN or PSO with NNA, with ANN, in fact. So artificial neural networks are capable of learning. So we train the ANN to show us what is the best prediction of these input solutions. For example, these input solutions, we already gave some data to the ANN. This is the input, this is the target, this is the input, this is the target, something like that. This is 1, this is 10, this is 2, this is 20. So for example, at this time I want to guess what is the value of 0.5. So in case, for example, we expect to have this kind of solution, 15. After training the ANN, we expect to have 15 as a result of the ANN. So this kind of prediction, estimation. So as I mentioned, ANN tries to map the input data to the target data by iteratively. For example, after 10 iterations, 20 iterations, try to map the input data to the target data. But we should be careful. This kind of map, it should not be the 100%, because after that we call it the ANN is overfitted. So we should not learn a lot. So this is talking those were about the ANN. So how about the neural network algorithm? So how we can convert the ANN to the neural network algorithms? Actually, the name is very general. If you search in the Google neural network algorithm, you can see many applications of ANN. So, but I was thinking about the name. Finally, I decided this name is the best name to describe the algorithm. So that's why the name is NNA. As I mentioned, the NNA tries to map the input data to the target data. So in fact, we are trying to reduce the error among the predicted solution and the target solution by iteratively changing the weight values. However, in the optimization, we don't have target data. In fact, our target data is the minimum value. So for sure, we don't know the minimum value. So that's why we are searching, we are optimizing. So in optimization, the goal is to finding the optimal solution. In fact, if the problem is minimization, the aim is to find the minimum value of the objective function. And also, this minimum function should be feasible, and we should have a defined strategy to find the optimal solutions. So, in fact, in the NNA, the best obtained solution at each iteration is assumed as the target solutions, and the aim is to reduce the error among the target data and the predicted solution, which is the best solution at each iteration. In fact, we are trying to move other solutions to the target data. It's this kind of movement. We are trying to move the solution and the other input solution to the target solutions. In fact, to reduce the error between the input data and the target data. So at each iteration, our best solution is our target data. So our goal is to reduce the distance, or not distance, maybe distance, but maybe objective function, in order to reduce the objective function between the input data and the target data. And in fact, the NNA concept is based on the minimization problem. So other optimization algorithms, NNA is a kind of population-based algorithm. So in fact, they have a population of solution pattern or pattern solutions. So our individuals are so-called pattern solutions, same as ANN. So, and the best obtained pattern solution is so-called target data, which is our best solution in the population. And we are trying to reduce the error between the target solution and the other predicted solution by changing the weight values, and also by changing the location or position of each pattern solutions towards to the target solution. So we have two items to change: changing the weight values here, and also changing the position or location of each pattern solution. So talking about the formulations, so we have a population of pattern solutions. You can choose the number of population, like 50, 30, 20, 100, with dimension D. For example, you have a problem with D dimension, and here is a population of pattern solutions as the initial population. For example, we have a D dimension here, and we have a number, for example, N pop, number of populations as the population size, and we randomly generate this initial population between the lower bound and upper bound. And so there's no bias, so just randomly between the lower bound and upper bound, and then we calculate the cost function or objective function of each individual here, and then we sort the population from the minimum to maximum, and after that our first solution, which is the minimum solution among the population, is considered as target data, and the rest of the solutions are considered as predicted pattern solutions, in fact. So yeah, the NNA resembles ANN, having N input. In fact, NNA is a kind of ANN with having N pop input data, having D dimensions, and only having one target solution and one response. I explained here. After we determine the target solution among the other pattern solution, the target solution, which is the minimum value among the other populations. After we setting the target solution, we find what is the target weight. In fact, we have two matrix: weight matrix and target solution and population matrix. From the weight matrix, the weight corresponding to the target solution is also selected as the target weight. So the target weight is corresponding to the target solution. At the first iteration, so whenever we find for example, our target solution, for example, individual number 23 is our target solution. So just in case for the first iterations, our initial weight matrix, which is randomly between 0 to 1, the index number 23 is considered as target weight because it is the weight it is corresponding to the target data. So we just randomly for the first iteration we choose, for example, individual number 23 at the target weight also. And then we proceed to make the weight matrix here. As you know, in the NNA, the artificial neural or the computational method units or processing units, they have some paths. This kind of paths considered as a weight, and we can, for example, strength one pass or weakness one pass depends on our reach. We can proceed in which way, for example. So in this case, back into the NNA, initial weights are defined like this. We have this kind of weight matrix here. So the size of the weight matrix is npop times npop. So it's like if you have 50 population, this size should be 50 times 50. So because for each individual you should have at least 50 value for the weight matrix. In fact, for example, V11, or here we can see V indexes subscribed by 1, that means for individual 1, this is for one dimension. For individual 1, this is for dimension number 2. And this is for individual 1, this is for dimension npop. Because you may have several dimensions. So in this case, this kind of weight is related to the neurons between the neurons. So in fact, if you have 10 neurons, your weight matrix should be 10 times 10 in order to have communication with all the neurons. So I mentioned about the design dimension, but this is not regarding to the dimension. It is regarding to the number of neurons. So if you have 10 neurons, your matrix should be 10 times 10 because for each neuron you should have a weight. For example, this is weight for neuron 1 to direct. This is from neuron 1 to the neuron 2, neuron 1 to the neuron 50, for example, or neuron 10, something like that. So it's a square matrix. These numbers are generated randomly between 0 to 1 during each iterations. So as I mentioned, the first subscript regarding to the pattern solutions, and the second subscript, the way of weight is related to the other pattern solutions in fact. So, but after that, I may notice if I use this kind of weight matrix, so the results are not very good. Because I noticed that the value of the weight matrix is very large sometimes, like 10, 20, and other values are very low, like 0.2, 0.1. So then I was thinking it's not a scale. So I should scale all the values of weight matrix in order to not acting a bias. So in fact, I made a kind of constraint for the weight matrix. So the summation of all the weight matrix at each column should be 1, and also the value of each weight matrix should be 0, between the 0 and 1. So in fact, using this kind of constraint, you don't allow the value of weight go large value. Without this constraint, so the weight values tend to grow very large, and in fact, in this case, it may stop in a very local optimal point. So in this case, we cannot search other area because this kind of way is a very biased way, and then the algorithm just wanted to follow this way. So that's why we should kind of act unbiased to let the algorithms to check other approaches. So having this constraint gives the NNA individuals controlled movement with mild bias, so varying from the 0 to the 1. So So this kind of constraint we should always follow, and in our formulation, in our coding, we should be careful about this kind of constraint. So we go to the code, and then we can see this kind of constraint after the weight matrix. So after that, after forming the weight matrix, our new pattern solutions should be calculated based on the this kind of equation you can see in the NNA. So the weight matrix times the input data. This is the input data or pattern solutions. So the weight matrix multiplied by the input data. I like matrix multiplications. So, and then after the matrix multiplications, we can have a new x. New x, that means still is not pattern solution, just x new. And then after that, we update the x new by the current position, and then we can generate the new solutions or new pattern solutions. So in fact, we generate the new solutions, and then after that, we plus to the current position in order to have the new position of the pattern solution. So I want to give an example here because maybe it seems very confusing to you. So I want to make it clear, at least for one individual. So if, for example, if we can assume that we have 6 pattern solutions. In fact, our population size is 6, and we have 6 neurons, and we want to update the first new pattern solution based on this equation. So x new 1 is like this. W11 times x1t, W21 x times 2, W31 times x3 plus W41 times x4 plus W51 x5 and plus W61 times x6. So this is for x1, the solution number 1. Here I have a very good example explanation here. So this is only for one dimension. Okay. Listen to me, this is very important. This is only for one dimension. So it's, in fact, here my input data to our initial populations from, for example, we have 6 initial populations, and here we have a weight values W11. This is W21. This is regarding that 2 is regarding to the initial number 2. 1 is for the first neuron. 3 is regarding to the neuron number regarding to the individual number 3, and first 1 is related to the first neuron. That's why we have a 6 by 6 neuron. The weight values, the matrix weight is 6 times 6. That's why we have a 30. Here we have a 36 values for the weight matrix. So I want to update this value x11. This is now x11, and this is new x11. How? Like this. x11 times W11 plus x21 times x21, x31 times W31, x41 times W41, and so forth. And then you can find the summation of these all values to x11, because the x11 new is the kind of average of these values, you can assume like that, by multiplying weight values, something like that. In case these kind of values after iteration change, so they can update, they can transfer to the target data, which is the best target. So I think you may know about this kind of process. So you can do this for x12, like x13 for d dimensions. This process happens in these equations. This process happens in these equations. These equations gives the x1 new, and then x11 new plus to the x11 old or current gives us the x11 updated, in fact. So in fact, in developing optimization method, we should think about how we can define the strategy for updating the position of the notions. This is a big deal in PSO, in GA, in ACO, how we can define a strategy based on nature or based on physics, everything, to define a very efficient updating position or movement position. You should think about this whenever you are going to improve your algorithms, whenever you are going to, for example, develop any optimization method. You should think about this equation. And this was inspiration for me to use the structure of ANN in order to generate new positions for the individuals. And also after creating the new pattern solutions from the previous pattern solutions, the weight matrix also should be updated. this kind of updating formulation is based on the target data and the current position. It's similar to the somehow there is standard updating position. For example, I want to update this weight matrix very close to the weight W target. So I just use this kind of formulations to update the weight matrix, and then I should be careful about the constraint of the summation should be 1, and all the values in the weight matrix should be between 0 and 1. It should not be greater than 1. It should not be smaller than 0. This is very important, because if you don't use this code, then you may not get a good result. I tried it before. I was noticed. So there's however, there's some unbiased approach if I remove this, because sometimes the value of weight matrix goes to 10, 5, 6, 5, other value to 0.2, 0.1, and in this case you cannot get the global optimal solution. And after that, so this kind of formulation is regarded to I can say that are related to the exploitation phase. Talking about the exploration phase in NNA, as you may know, in artificial neural networks we have a bias operator. And what is the performance of the bias operator in ANN? In fact, bias operator is considered as a noise to the network, to the computational model. So in this case, I inspired, so we can use the bias operator as a global search operator for exploration phase. That's why we try to modify a certain percentage of the pattern solutions as a noise, and also for the weight matrix we are going to change, because this kind of noise acts to the weight matrix and also acts to the pattern solution as well. So in fact, in the bias operator, we are trying to explore the search space, and this kind of operator acts as a mutation operator in the GA. In fact, we are trying to change some of the design variables of the pattern solutions and also weight matrix randomly between the lower bound and upper bound. This is a kind of noise to the system, and this kind of instability it makes us to search more region in the solution space. Here is the method we used, the suggested strategy for the bias operator to a new input solution and also to the weight matrix. So from the population from 1 to the number of populations, we here define a value which is called beta. Beta, we call it modification factor, which determines the percentage of the pattern solution that should be altered, should be changed. In fact, the initial value of the beta is 1. That means at first iteration, 100% of all individuals should be changed. That means totally the individual is changed at the initial phase, and this value reduces at each iterations to switching or switching to the exploration phase. At first this value is 1, that means at the first iteration we are here. By iteration goes, the values of beta is reduced to 0, and at the final iteration we are in the other operator. So at first, if the rand is randomly numbered between 0 to 1, is smaller than beta, which for example at the first iteration beta is 1, then we are here, then we find the number of the design variables should be changed. For example, if the number of the beta is 1, the dimension is here is 10, for example. Then NAB, number of the biased variables is 10. That means all the design variables should be changed at this phase. So, and then with the X input randomly generated between the lower bound and upper bound, and 10 times for the 10 dimension, we change all the dimensions. And this bias is for new pattern solutions, and this again we apply bias to for update weight matrix. In this case, also we calculate how many of population should be changed. So in case if beta is 1 at the first iterations, in fact all the weight matrix should be changed. So we change the number of values between the 0 and 1 as a bias operator. But you can use other operators, other global search operators in this phase. but this is the way I was thinking, similar to the ANN, because as you may know, in the NNA, ANN, sometimes noise acts in one neuron and change the value of that neuron. So that's why here, based on the value of beta, we can change the value of the design variables, and by iteration goes, this value reduced and finally reach the value of 0. So after after creating the X new and also updating the weight matrix and also applying the unbiased operators based on that conditions, so we have another phase based on the ANN. We have a transfer function, and in fact the transfer function in ANN transfers the new pattern solutions in the populations to the current in the ANN, the transfer function in fact mapped the input data to the output data by kind of equation like sigmoid equations, linear equations. But here in NNA, transfer function acts like the movement equations. In fact, the transfer function moves the pattern solutions from the population to the best obtained solutions and moves their position from place to another place towards the target solutions. As you can see here, the already updated pattern solutions. So based on the transfer function operators, gives us the X star. The X star is like this. The current position plus this value. Very small, very simple updating equation from the current position to the target solution. We can use this kind of simple transferring equations. In fact, here we are going to, after the modification based on the structure of the ANN, we are going to move the current individual to the solution, which is our best solution so far. So this kind of equation is very critical for every optimization method. And finally, we should move every individual to the target solution. So you can see this kind of equation in many algorithms and the kind of overlap between among the optimization algorithms. So this is the combination of the bias operator and transfer operators. Here you can see that, for example, if rand smaller or equal to beta, then we are in the bias operator. Otherwise, we are transfer function. So if in fact here, that first iteration for sure we are here because the value of beta is 1. At every iteration we are here. But when iteration goes, so the beta is going to reduce the value. So it's going to be small. So then maybe at the final iterations or iterations, you are here and transfer function here works. And for sure in the final iteration the value is very small. So the small number of design variables change in this space, and mostly we are in the transfer function, and here act as exploitations, and here act as iterations. So that's why we don't need to fine-tune the value of beta, because the value of beta is starting from 1 to the 0, so no need to add any user parameters to the neural network algorithm. So here the sequential steps of the artificial neural network. We start with the pattern solution from 1 to number of population size. First, we are defining our weight matrix. After the weight matrix, we can from here we select our get data. From here we select our target weight. After that, we generate the X new, and then we update the X new, and then we update the weight matrix. After that, based on these rules, we may proceed to the bias operator, or we may proceed to the transfer function. After that, we calculate the cost function of X star. If the X star is smaller than the target, then update the target. Also update the weight matrix, because at each iteration we should also update target weight, because the target weight also is very important, because in each step we always multiply the weight matrix to the X, the current position. So when we update the target solution, we check the stopping condition. If it is satisfied, we record the target solution, which is our minimum solution or optimum solution. Otherwise, again, change the weight and then X new, and then the process repeats until the stopping condition is satisfied. And here is the schematic view of the NNA having the feedback, self-feedback and global feedback. Here we can see here In this case, for example, these are new solutions, our improved solutions for population here in population, in fact, and each neuron, each input data have weights like W11, W12, W13, W1, W in pop3, and then here, sorry, W1 in pop, yeah, W1 in pop. This is for this. So W11, that means individual one for itself. W12 weight for individual 1, 2, individual 2. W13 weight for individual 1, 2, individual 3. W1 n pop means weight for individual 1, 2, n pop. That's why we have a n pop times n pop population. I mean, the size of the weight matrix is n pop by n pop times n pop. Then we are here as a summation multiple by the weight matrix multiple by x input. We have x mu, then update the weight matrix, and then we have a transfer function or bias function as like this selection. Selection here means find what is the best value of the, what is the best value, because we compare this value with the cost function. Then we have self-feedback. Also, we have a global feedback here. In this case, we have a combination of self-feedback and global feedback in order to find the optimum solution. And here is the flow chart of the NNA. Also, you can see it in our papers. So I already explained about the steps, and these are the descriptive steps of the NNA. So here we choose the pattern. So our initial parameters are only the population size and also the maximum number of expressions or number of function evaluations. We randomly generate the initial population between the lower bound and upper bound, calculate the cost function, randomly generate the weight matrix between 0 and 1, select the target data and also its corresponding target weight, then generate the new pattern solutions after that, and update the pattern solution. Generate a new solution means x new, and then update the pattern solution, that means plus the current position, and then update the weight matrix considering its constraint. Check the bias conditions. If rand is smaller than beta, then perform the bias operator. Otherwise, perform the transfer function operator, and then calculate the objective function for all updated pattern solutions. Update the target solutions and its corresponding the target data, target weight, and then check the stopping condition. So yeah, these are the process and strategy of neural network algorithms. We are going to show these kind of steps in the MATLAB code. I'm sorry, I have only MATLAB codes here, so in future I will share the code in C++, Visual Basic, and Python, and other programming languages. So sorry about that, my code are in MATLAB now. So these are first published papers. I had this honor to work with from Dr. Anupam Yadav. Actually, Dr. Anupam Yadav helped me regarding the mathematical point of view. Actually, in this paper, we already proved the convergence rate of NNA in mathematical point of view. So it's a very nice work done by Dr. Yadav, because as you know that finding the mathematical proof behind of each optimization algorithm is not an easy task to do, and NNA has this potential to show mathematically that it finally converges to the solution based on the mathematics proof. So at the end of this paper, in the appendix section, we mentioned about this concept. And so far, there are published like not many more, but like 6 to 7, 8 papers regarding the NNA, like hybrid teaching TLDO with the NNA, and also using Drake optimization algorithm with NNA, like application to the economic load, these other applications, and also fuel cell. Actually, I did not. We just published one paper so far. So because I was busy these days, I couldn't publish more papers in neural network algorithms. So this is a website. You go to the website and download the codes for unconstrained version and also constrained version. So far, I did not develop the multi-objective neural network algorithm, so it's a very good chance to check the performance of an NNA for multi-objective optimization algorithm for the benchmark, for the applications, So I suggest also to compare this algorithm with the water cycle algorithms and other optimization methods. If you want to publish more papers, is a kind of comparative study, or you can improve the NNA using some other updating equations, like we updated the weight matrix, okay? But you may use some of the idea used in ANN for updating the weight matrix, because there are many strategies in updating the weight matrix in ANN. I forgot the names, but we mentioned this kind of improvement in the paper. So, but you should be somehow expert in ANN, because for me, which I'm not very expert, so it's hard for me to find out what are those learning or updating equations. So if I want to put the NNA, I will put the NNA in this area, which is a base materialistic, naturally inspired, and it's similar to the PSO. It's a kind of implicit optimization method. Let's see. If you want, I can go through to the codes if you are interested, or if you have time, I can explain the code. Also, I already written the code here. So, so same as the LWCA, we have an objective function. Is there any question?
There is a question from Sushila Vishnoi. How to select the value of beta?
Silicon value of
Beta.
the value of beta at first, the initial value of beta is set to 1 at first iteration, which it means 100% of all individuals in population change. And then after iteration goes, the value of beta is going to very small values like 0. So there is no need to change the value to select or to choose the value of beta at the beginning of the optimization. So the value is starting from 1 and ending to 0, something like that. So no need to change. Okay. Here we mentioned the beta is 1, and finally beta reduced. So there is, because at first all the individuals, the bias operator applies to all individuals, all the design variables. So in this case, we may have this chance to lose some of the individuals from the initial populations, but in fact, it shows that we may have better global search by iteration goes. Okay. If there are more questions, I will be happy to answer. Otherwise, we can proceed to the codes here.
Dr. Jatinder has a question.
Okay, so
Dr. Ali,
yes,
we can
yes,
take a
yes.
question here. Dr. Jatinder, are you
Yes.
there, or shall I ask a question on behalf of you? Okay, let me read. Why new pattern solution and updated weight matrix solutions share the same beta number of solutions in the bias operator mode? Can't we have two parameters, namely say beta and alpha, to control the number of patterns? Dr. Ali, can you read this chat?
And yeah. Okay. I let me see. How can I? Okay. Let me. How can I see the chat?
Please press escape
I
button.
can. Here, there's a stop sharing and hide. If I stop sharing, you cannot see.
Press the escape button. Means you.
Oh, here. Okay. Yes. Okay. I just noticed that. Is there any criteria to give you this? So where is the question? Why new pattern solution and updated weight matrix solution share the same beta number of solution in the bias operator? Can we have two parameters, namely say beta and alpha, to control the number of? I think there is no need. I mean, because what is our goal? Our goal is to alter or to change the value of weight matrix and also the number of design variables. So I think there's no need for that. You can also, but because we start from 100% of all design variables to 0, so that means if you say alpha also can be start from 1 to 0. I mean, there is no, difference. Actually, this is the standard NNA. I mean, for sure, I'm expecting to have more improved version of NNA. This is a very rough idea of how to convert artificial neural networks for solving the optimization problems. So you may check other possibility, for example, but my suggestion is to try to not add user parameters to NNA, except that population size and also maximum number of iterations, because this is one of the strengths of neural network algorithms like TLBO. TLBO also does not need any initial parameter. NNA also does not need any initial parameters. So that's why if you are going to add parameters, in case it's better to not add any user parameters. But in case, for example, you say that okay, I add one user parameters, but greatly I improve the results. In this case, okay, that makes sense, no problem. But for the same result, same performance, it would be better to not add any user parameters. But I think there's no need for defining beta and alpha for the both like weight matrix and pattern solution matrix. And weight matrix created correctly. Yeah, that was my answer. Is there any criteria to give value to synthetic weight? Is there any criteria to give value to synthetic weight? Actually, the value is like that. The concept is like that. Okay, how the XNew is created and how the XNew gives us the cost function value. So which is the important things? The weight matrix, the importance of the weight matrix like that, that multiplication of weight matrix and XNew gives us the X updated, and then when we calculate the X updated and we see that, oh, this value is very minimum, so in this case, that weight matrix should be noted as target data, because that weight matrix, that weight value was the best weight value. So that's why we call it target weight, and we force all the weights, all the values of the weights move to that target weight to, for example, exploit more better solutions near to that region. That's why the concept was like that. Um, I hope I could answer the question. Okay, so there are many applications of NNA. You can use it actually in future in application, because I noticed that for very complicated optimization problems, the performance is very good. I personally witnessed this advantage also from the published paper. I noticed that when the number of design variable increases based on the unique structure of the NNA inspired by the ANN, it can generate better solutions based on these kind of structures, neuron output, input data. So for the larger scale, if you give enough maximum number of iterations, your solutions would be high quality solutions. So I think there is no more question here as I see here. So I think I can proceed with the code. Similar to the WCA, here there's the input objective function, your objective function, lower bound, upper bound, numbers, number of population, maximum iterations. And there are outputs of the NNA. What is the optimum solution? What is the cost function or objective value of that solution? Number of function evaluations used, and the time elapsed, something like that. If you don't put this value, the default value would be 50 for population size, and this kind of number of this value for the maximum number of iterations. So you can see this like in CEC competitions, like 5,000 times to the design variables, and I divided by number of population to make it as a maximum iterations. So in this case, we first initial the population size or its pattern. Its pattern is the solution pattern. I mean, its pattern is the same as a solution pattern. So we generate solution pattern between lower bound and upper bound randomly, and we calculate the cost function here, and then we sort the population from the minimum to maximum, and then find the value of the cost function, the minimum one, and the index of the minimum value. Okay. Let me here. I forgot to. Let me. Okay. Oops, it's not working. Okay, So okay, then LB time. Mm, Here number of inverts is like we have, for example, 100 number of inverts. Here lower bound is like 10, and upper bound, sorry, minus should be minus ones. Here should be minus 10. I want to do the same as the water cycle algorithm. So what else? And here, okay, we have 100 dimensions. So I make a function here. So this would be, I already removed that function, so that's why. Sphere is my function. Sphere is x as input solution. So something like that. A global inverse, and then for I from 1 to inverse, z dz is equal to xi to the power 2. Z is plus z, and then oops, z is equal to 0. Oh, is this correct? Yes. Very simple sphere as well. And that's all. So we have a function here, x1 power to 2 plus x2 power to 2 plus x3, something like that, for 100, for example. And this is number of inverse, 100, and this is the global inverse, and that's all. And then I can put here NNA, copy and paste here. Then, okay, that's all inverse. And a pop should call it, okay, 50. It's okay. That one is like 1,000 population size. That's okay. Then that's all. So we can start. Let's see step by step. Go inside, step in. So here until here. Okay, we have here minimum cost is 100. What happened? What happened here? Minus, okay, this one should be 10. This one should be 10. The upper bound should be minus, lower bound minus 10 to the 10. Then step in, and until here, you can see that, okay, this, for example, the minimum value is 2,800. And this is the X pattern. X underline pattern is like this. X underline pattern is like it's like this. So the minimum one is the index. So for example, population, the individual number 40 has the minimum value, which is 2,800, and the index is 40 out of the 50 cost here. Okay. So after that, we are going to, this is our initial population, the cost, so the individual number 40 now is our target data. So here we mentioned the index 40 is our X target, okay, here. And then corresponding, the weight corresponding to that individual also is called W target. So here we create the initial weight matrix. So for this weight matrix, I wanted to be the summation of each column should be 1. So based on this equation, which is Dr. Anupam's also suggested, we calculate the weight matrix between 0 to 1. If you can see that, okay, let me show you here. The weight matrix here is W, okay, it's W, yes, it's W. So if I mention W here, actually 50 dimension is too much. Okay, sorry me, let me try with 7 to see the performance better, because otherwise it would be very huge. So until here, okay, until here, W is like this. W is like this, but dimension is too big. This dimension, number of the variable is 7, okay, but because we have 50 populations like this. So W is like this. If you can see here, W, I show you here, W is 50 by 50. See, this is W weight matrix. Is somehow, so between 0 to 1, and some of the value are very small, some of them are very big. And then if I summation of W, it should be 1 1 1. So the summation of each column should be 1. And that's why when we generate the initial value, initial weight matrix, so the summation of the all columns is equal to 1. So we should obey this rule. So then you can see that here, for example, the index number 47 is the minimum one. The cost is 90, very because we have 7 dimensions, so 90 is okay. I said, oh, okay, for 100 dimensions, the best is 90. No, it's not like that, because our number of dimension is 7, then okay, 90 is okay. So then X target should be this kind of, this is the X target with index 47. The cost, the minimum cost is the target. This is the target, means the target solutions, the cost. This is the optimum solution so far, the best obtained solution so far. And this is the weight target corresponding to the index number 47. And this is a the target data, the weight target or target weight, something like that. So far we are here. So then we proceed to generating the X new. X new is the time, the W times the X pattern, the input data. So this is the X new, and then we add this X new to the current X pattern. So that's why I use the new notation here, the new parameter here, to add the X pattern, which is here, to the X new. Then we have the updated X pattern. So the updated X pattern. So then after that, we update also the weight matrix based on this equation, as you see in the PowerPoint. This is the weight target. This is a 2 random, and also we can, for each weight, we updated for 50, in fact. We come here, we updated the weight matrix, and then we should check for the summation of each column should be equal to 1. Here we should check, for example, if I come here, then you can see that again the summation should be 1. So the summation of W is 1 again. Summation of W is now 1 again. You should be careful about this summation. So now here we check, after the updating the weight matrix, the summation of each column should be equal to 1. Then we go for the create new input solution for the bias operator and weight and transfer function operator. For the bias operator, here for each population, in each individual, we check the beta. Beta is 1. Here for sure we are in this step here for the bias operator for input solution. So how many how many number of design variable should be changed? Here is like 7. That means, okay, at first number of design variable was 7. In this case, 7 design variable should be changed because the beta is 1. So okay, for the 7, I just randomly generate one solution between the upper bound and lower bound because I need to select 7 out of here. So this is the rotate position. So I want to check the rotate position. For example, I checked here, the usage of randperm. Randperm means that if randperm 7, that means randomly give you the order like 4, 5, 7, 6, 2, 1, 3. That means location 4 should be changed based on should be changed by -4. Location 5 should be changed with -6.02. Location 7 should be changed with something like that, 8.63. This is the order, which is totally random. Okay, this is rotate position. Rotate position. Rotate position means the rotation from 1 to the number of rotated, from 1 to 7 here. So here, for example, number of rotation, 7 rotation for each pattern. From individual, 1, because we are in the loop 1. 1 is for individual 1. For individual 1, we have a rotate position from here. M started from 1. This is 1. Which one? The number of 1. So, for example, here we can see here -4.20 here. Here -4.20, and then we can do this the same until to 7 times till to the 7 repetition we can modify here. And this is for X pattern, and also we have a bias for weights. Same strategy, exactly the same strategy until here. But we should also again check the summation of each column should be equal to 1, okay, in case if we are more than, and then uh, okay, jump, because here we are not in this here, then that's why it jumps. So after that we are here. Let me, we are here because we are not in this phase, because the beta is 1, and then for the all the individuals in these iterations we are in these sections. So that's why we are not here. And after that, when 50 pop finished, we should reduce the value of beta by any reduction formulations. So this is the suggestion reduction formulations. The value of beta should be now, for example, now for the next iteration, the value should be 0.98 based on these equations. And based on the experience, values smaller than 0.01, which is very small, because after that there is sometimes you don't have any how can I say, any improvement for the bias. In this case, if your beta is smaller than 0.01, then set the value of beta 0.05, and then again from 0.05 comes to 0.01, then again 0. Like the same repetition of the beta. Otherwise, you can also use this kind of equations, which start from 1 and finish at value of 0. This kind of formulation based on the maximum number of iterations, and this is the current number of iterations. And then you check that you reduce the value of beta here, and then check all the pattern solution are between the lower bound and upper bound, in case if you already violate the lower bound and upper bound, and then find the calculate and then calculate the objective function of each pattern solutions after the updating, after the bias, after the transfer function. Then you find the value of each for 50 times, and you come here, you can see here, and now you have this kind of value. So then find the minimum cost. So this is the cost, find the minimum. The minimum is now 53. Out of from 90, we now comes to 53. The objective function is now 53. In one iterations, we moved from 90 to 53, and the index, the best is number 17. And then if the cost is smaller than 90, then change the target. I mean, the FF should be target, and the also the index should be the X target, the index 17 should be W target. Otherwise, because we already, why we do this? Because we already lose our X target, because we already copy all the pattern solution inside the pattern solution. So we don't have any copy of our initial population. That's why we need to have the X target in case of else. I mean, here is okay. Here we already updated the target, no problem. But in case, if for example FF is not smaller than target, in case we say that, please find the maximum cost and the index, and then put the X target, and I mean, how can I say, substitute the X target into the population size, but instead of the maximum solution, instead of the worst solution. And then also do the same for the weight target. In this case, for every iterations, otherwise we have the improvement, otherwise we have the X target in the populations, the so far X target in the populations. So this is the good things, actually. This is the good things. And then after that, display the iteration objective beta, and also save the best solution at each iterations, and then plot and other things. So if I do this, I continue. Let me remove these red circles, and we can just proceed. So this is for like 7 dimensions, so it's not a big deal. So you can see here the value of beta is going to reduce from 1 here, from 1 to like 0, almost 0, but in case 100 like put 2000, you can see in case See, when the value of beta is smaller than 0.01, again the beta is 0.0, again, like, can I go up, goes like many 100 dimension. So here, see, the value of beta is smaller than 0.0, then again the beta is updated to 0.05, then reducing to 0.1, then again the value is updated to 0.05, something like that. So yeah, this is the process of NNA. But I suggest to uh, use number of enough number of population, enough number of maximum iterations for. I want to open my. Let me. Where is my box? Oh, not in 2018. So here we can see there is some point I want to make it clear. So in this case, you can see for the convergence rate, you can see at early iterations, the blue color is related to the NNA. You can see that early iterations, so the convergence is not very considerable. So that means that the NNA at the first iteration tries to like search more area, then suddenly step by step convert to the minimum value, and sometimes find the better values than other algorithms. Like you can see here, the NNA starts from here, but for example, this is number only 200 iteration actually, but this is kind of just showing for the small number of iterations, but for sure it's more than more than 2,000 iterations. But I just wanted to mention about only 200 iterations here, only for this is for dimension 200 for 200 iteration number. In fact, in this case, it shows that at first iterations, the global threshold of the NNA is very high. You can see when we are in this area, that means the algorithm is not very hurry to find the global point, because he wants to take its time to search more areas, then slowly converge to the optimal solutions, and finally at the final iterations, even the cost is better than other optimizers. You can see here this is for 200 iterations, but it is continued to 1,000 iterations or 2,000 iterations, and finally the result is better or sometimes at the same with the other optimizers. So in this case, this is the unique structure. You can see, like for the all algorithm, we mentioned about this point in the paper, why we can see this nature for the NNA. Yes, like this. Yeah. Okay, so I think after that, yep. Let me see if there are any questions.
There is only one question. You can answer quickly, and then I can take over.
Yes, I can read the question here. Actually, so far it's combined with TLBO, Gray Wolf optimizers. It can be combined with harmony search algorithms, because as you can see, the harmony search has a harmony memory. If we use this concept of NNA into the harmony memory in the harmony search, it would be nice. Actually, this is one of my ideas, but I still don't have time to work on it. But I'm sharing this idea with you. If you're welcome to use this kind of hybridizations and apply to the CEC optimization problem, real life applications, in order to publish papers, and also in order to improve the performance of both NNA and HS at the same time. The criteria, I can say that the NNA, the exploration phase is very strong. As you can see, it starts from the top. That means it's good. When you can see the algorithm start from the top, that means it is going to search the other areas. It is not in a hurry to find for example, global point, because when you are in a hurry, the chance of getting trapped in the local optima is very high. So for the same number of function evaluations, okay, you need to uh, design it some spaces, some iteration for global search and some iteration for local search. If you very suddenly convert to the near local solutions, it is not a very good aspect of the algorithms. And one thing is the NNA needs some iterations to reducing the beta. I mean, for in case, as you can see here, for example, for iteration until iterations 800, so the value of beta is still not very small. In this case, you need to increase your iteration number, but your number of function evaluations should be fixed. For example, I have 5,000 function evaluations. Okay, I can go for 100. I can go for 50 populations and 200. I mean, I said 5,000. Okay, I can use 250 iterations with 50 populations. Is it right? No, it's not right. 20. Okay, 20 populations with 250 iterations. In case, so it should be like this. You should not use 50 populations with 100, for example, iteration, because we should give time for beta to reduce until some predefined iterations. After that, we are in the exploitation phase, because sometimes people set the population size for 50 and iteration number for 100, and then they say, oh, the result is not good, because the beta needs time to reduce it after some iterations. So I don't mean that, okay, NNA needs more function evaluations to calculate the objective function. No, you should just increase the maximum iteration number. No need to increase the function evaluation number of function evaluations. The number of function evaluations is fixed, but try to increase the maximum iterations and reduce the number of populations. Even with the population number 5 or 10, you can get the good result, something like that. So I can see it. And then is NNA used to solve the water division? So far, it is not used actually. Like so far, there are 7 to 8 papers related to the like energies, fuel cell, something like that. So there's no application of water cycle algorithm for water distribution systems. It is combined for better performance. I mentioned that TLBO. I mean, other like harmony search, PSO, I think is good, because PSO also can be. The exploration is good in NNA. Exploitation also, my idea is also good, to be honest. I mean, comparing to water cycle algorithm, I can say that NNA is better, because that is why we published in other papers. Otherwise, why there's a need when I see the two algorithms are the same performance? Why should we publish more algorithms? In case when you notice that your algorithm is better than the previous one, you may publish it. Otherwise, don't waste our time. We should not waste our time developing another algorithm with the same performance. My personal idea is NNA is better than the water cycle in terms of the exploration and also exploitations, as we can see in the paper, in terms of the statistical test and statistical result, comparing even to the TLBO for the same number of problems we applied. We find the better solutions. And also DE is one of the best algorithm, actually, to be honest. DE is also good, but okay, DE is also a good one. Here you can see the NNA in terms of the Friedman ranking. The NNA is the rank number 1, and then rank number 2 is D, and almost close. And rank number 3 is like TLBO rank with the differences is almost high. Rank number 4 is GSA, like other, you can see the ranking of other optimizers. So in this case, D is also a competitive optimization method. Also consider it for your optimization problems. So you may also hybridize the NNA with the DE as well, and benefit from the both advantages of NNA and DE as well. So are there any questions? Is there any questions?
I think there are none. Dr. Ali, thank you for your lecture. And please stay with us because I'll cover gravitational search algorithm and it'll take a while
Yeah,
because
sure.
we'll wind up very quickly. And I want you to stay connected with us while the finishing of this program. So you may stop presenting and I'll
Yeah,
start
sure,
from
sure.
here.
Yeah, sure. Thank you very much. Thank you very much, professors, doctors, and students here. Sorry, I my English for the NNA is not very in a good way because I'm still not very expert presenting NNA in a good manner. So just excuse me and sorry for sometimes I my English was very bad in terms of grammar. I already noticed that, but yeah, I try to improve. Okay, thank you very much.
Thank
Okay,
you.
have a good day. I'm here still with you guys and listening to Dr. Anupam Yadav regarding to the gravitational search optimization algorithm.
Now are my slides are visible? I hope all of you can see my slides. Okay, so I'll begin quickly. For those who are new to me, I'll take the opportunity to introduce myself. I'm Dr. Anupam Yadav. I'm assistant professor in Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, and I'm one of the student of Professor Kusumdeep. Here,
Sorry to
The lights are not
slides are
visible. Slides.
slides are not visible.
You know,
Okay, can you check now?